Well, here we go with lesson 31. This wraps up section 8.3. We're going to spend 2 days on it, however. We're going to discuss how to do airplane problems. In today's lesson, we're going to look at how to do them using the parallelogram method. In lesson 32, we're going to do the same problems using the vector method. Here's the basic setup of all these problems. An airplane with an airspeed of so many miles an hour is flying in a direction of so many degrees, and a certain mile-an-hour wind is blowing from a certain direction. And we're going to approximate the true course and ground speed. That's the basic setup. And now we can give you any two of those three and have you either work forwards for the resultant, that's the true course and ground speed, or we can give you the true course and ground speed and the speed of the wind and have you work backwards to find the airspeed and direction of the plane, or we can have you work backwards and find the wind direction, speed and direction of the wind. So we'll show you all about that. And let's get a reminder here about how we do airplane problems. All angles are from the north and they open to the right. They open clockwise. So normally we start with a point A and we go above it and we open to the right however many degrees. So we can get angles anywhere from 0 to 360 degrees. So the plane takes off. This looks like the plane's leaving at maybe 50 degrees. So we draw the vector for the plane as it takes off, and whatever the angle is, that's where you draw it. Then we put in the wind, and this wind looks like it's going 120 degrees or so. And so that's the wind. So the plane takes off, and then the wind hits it, and then the resultant, which we refer to as true course and ground speed, is somewhere between the two. So P represents the plane, W represents the wind, and R represents the resultant. And we refer to that as the true course and ground speed. That's what's really happening. And so you see that the resultant is equal to the wind plus the plane. That's how we end up with that. Now we're going to do parallelogram method. So we're going to duplicate the plane's vector, duplicate the wind's vector, law of cosines, law of sines. And to emphasize this again, when you see true course and ground speed, we're talking about the real direction of the plane and the real speed of the plane. This is what's actually happening. When you look up in the sky, you don't know what the plane's trying to do and you can't tell what the wind's doing. But if you had really good equipment, you could determine what the speed of the plane is, the real speed, the ground speed of the plane is, and what the true course of the plane is. That's what we're looking for here. So here's our first problem. An airplane with an airspeed of 300 miles an hour is flying in the direction of 60 degrees and a 50-mile-an-hour wind is blowing directly from the west. Approximate the true course and ground speed of the plane. Quite often we'll say that the wind is blowing directly from a direction, in this case from the west. So in airliner talk, that would be 90 degrees because these angles are coming from the north. So here's a sketch of it. The wind is blowing directly from the west, so that's 50 miles an hour at 90 degrees. The plane is going 300 miles an hour at 60 degrees. This is all from the north. And as we normally do, we're going to have to find the angle between the two vectors, and then we're going to need the angle supplementary to that. Oh, you're going to recognize this. So we complete our parallelogram, we draw the resultant in there, it's somewhere, it's right there at that diagonal. So our next step is to find the angle between the two vectors, and we do that with subtraction. So 90 minus 60 is 30, but we really don't want that angle. We really want the angle that's across from the resultant. And in parallelograms, consecutive angles are supplementary. So 180 minus that 30 degree angle is 150. We now have, look at it, side angle side, 50 miles an hour, 150 degrees, and 300 miles an hour. So we can now do law of cosines to find the magnitude of the resultant. And that'll be the ground speed. And you've seen it before. 50 squared plus 300 squared minus 2 times 50 times 300 cosine 150 degrees. Do the math. And I'll give you a chance to look this over, or maybe you need to pause it and use your calculator. But it all works out to 344 miles per hour. And that is the true course, or the ground speed of the plane. It had to be somewhere between the sum and the difference of the two. Had the wind been directly behind the plane, we'd be going 350 miles an hour. Had the wind been directly in the nose of the plane, we'd have been going 250 miles an hour. So our answer had to be between 250 and 350. 344 is pretty reasonable. Now we need to find the true course. Well, we know it's 60 degrees to what the plane was trying to do, and so we need to go alpha farther, that angle a little farther to figure out how far it is to that resultant, 344 degrees, so 344 miles per hour resultant. So I'm going to call that alpha, and I'm going to say 60 plus alpha will be our true course. That's the angle we're looking for. So we use law of sines. We say the sine of alpha over 50 equals the sine of 150 degrees over the resultant. And we multiply both sides by 50. Take 50 times sine 150 divided by the resultant. We end up with the inverse sine of 0.07263, which is 4.2 degrees. So the angle between the plane and the resultant is 4 degrees. So we add it up and we get 64 degrees. So the true course is 64 degrees. That's what the plane's really doing. And our ground speed is 344 miles an hour. And that's the actual speed, the real speed of the plane. All right, let's do another one like this and see how we do. An airplane with an airspeed of 350 miles an hour is flying in the direction of 210 degrees. Okay, so this is wrapping around there. And a 40-mile-an-hour wind is blowing directly north. Approximate the true course and ground speed of the airplane. So let's sketch it out first. And so you see there I've got the 350-mile-an-hour plane going at 210 degrees. That's past, due south, so we're a little further on there. And we have a 40-mile-an-hour heading due north. So in airline talk, the wind is going 360 degrees. You can say 0 degrees, but let's say 360 degrees. So the first thing we're going to do is find the angle between our two vectors. We always do that. So we sketch it out, and we see that we have the 350. We duplicate that up top. We duplicate the wind down at the bottom, and we now have a parallelogram. Let's find the angle between the plane, the 210-degree angle, and the wind, and I'm going to call that 360, because remember, we always want to find the angle between the two vectors first. So 360 minus 210 is 150. We really don't want the angle between the two vectors, do we? We want the angle across from the resultant. And in a parallelogram, consecutive angles are supplementary. So 180 minus 150 is 30 degrees. That's the angle we'll use in our law of cosine equation. So r squared equals 350 squared plus 40 squared minus 2 times 350 times 40 times the cosine of 30 degrees. And you work it all out, and the ground speed's 316 miles an hour. That is the actual speed. That is the true speed of the plane. Let's look for an angle and get the true course. So now I'm going to look there at the angle between what we originally wrote down for the plane, that 350 mile an hour one coming out of our dot there, coming out of our airport. I want the angle between that and the 316 miles an hour, the resultant. I want that angle because I know it's 210 down to the plane. I'm going to add alpha onto that, and that'll get us our true course. So we're going to use law of sine to find alpha. So the sine of alpha over 40 is equal to the sine of 30 degrees over the resultant 315.993. Multiply both sides by 40, inverse sine, and we get 3.6 degrees, which will round off to 4 degrees. We always seem to do these to the nearest whole degree. So the true course is the 210 degrees plus the 4 degrees, which is 214 degrees. Ground speed is 316. True course is 214. Back to that ground speed. Remember, it had to be somewhere between the sum and the difference of the two. So it had to be between 310 and 390. So 316 was reasonable. All right, let's move on. All right, let's wrap this up with our last example. Now, this one's a little different. The airplane pilot wishes to maintain a true course in the direction of 300 degrees with a ground speed of 450. So we're giving you the resultant. The wind is blowing directly north at 60 miles an hour. We want you to work backwards and find the required airspeed and direction of the airplane. So now we're looking for P. Let's draw it out. So the resultant is 300 degrees, and going 450 miles an hour. The wind is blowing directly north at 60 miles an hour. We're going to call that 360 degrees. When you draw your parallelogram, you got to keep R as the diagonal. So we don't draw the wind north at the end point there. We got to draw the wind south of that end point. See how that popped in there? So now we can draw our parallelogram. So now we can connect those endpoints between the end of the wind in both directions, I guess, the north side and the south side of that. And we can draw in, and what we're about to draw in will be the plane. Now the one coming out of the bottom, There it is. The one coming out of the bottom is the one we really want. The one on top just completes our parallelogram. And so there we have it. So you might have to go back through this a couple times and see how you make that diagonal, how you draw the diagonal in there and draw backwards to get the parallelogram drawn properly. So now we have to get the angle between the two vectors. We always want the angle between the two vectors. So 360 degrees minus 300 degrees is 60 degrees. There's a 60 degrees between the resultant and due north. That's all we need. Now we can do law of cosines. And so 60 squared plus 450 squared minus 2 times 60 times 450, cosine of 60 degrees. And we end up with the plane going 423.2 miles an hour. Now, we got that plane at the top. We got that red up top, but actually that's the same as the plane at the bottom, which is coming out of the airport, that dot there. So we know that the pilot was trying to go 423 miles an hour. That was the speed of the airspeed of the plane initially. Now we need to find an angle so we can figure out what angle or what direction the plane took off at. Again, this is a little different, so we're going to have to end up using subtraction on it. We know what the angle is to the resultant. We want to back up and figure out what the angle is to the plane. So alpha is the difference again, only this time we're going to take 300 degrees minus alpha because we want to know what direction did the pilot attempt to go before the wind pushed the plane north to 300 degrees. So we're going to use law of sines to find alpha. We always use law of sines. So the sine of alpha over 60 is equal to sine of 60 degrees over the resultant, the plane, 423.2. Multiply both sides by 60, inverse sine it, and we get 7 degrees. So 7 degrees is the difference between the resultant, which we know to be 300 degrees, and the plane. So we're going to take 300 minus 7 degrees and wrap this thing up. And so 300 minus 7 degrees is 293 degrees. So that is the direction the plane tried to go before the wind pushed it north. And the airspeed was 423, and then the wind forced it up to 450. There you go. So that is a working backwards problem where we give you the resultant, true course and ground speed, and you work backwards to find the plane. We could give you the plane and have you work backwards to find the wind. All right, that wraps it up. So I would like for you to use the parallelogram method to solve all the problems in this lesson. When we go into lesson 32, we're going to use the vector method to come up with this, to solve these exact same set of problems. Get to work.